is any who will talk again about integrating Python with a lot of constructs including logic. So going to talk about Alda. You're on mute.
Okay, hi. This is about Alda, a language that integrates logic rules with everything else seamlessly. And this has helped for lots of students and colleagues in grant support. Okay, so I want to use the logic rules because they're good for knowledge reasoning, especially for object relationships. And this is the rule. You can ignore these just for people who didn't know how to read these prologue looking rules, right? There is a path from X to Y if there's edge from X to Y. There's a path from X to Y if there's edge from X to Z, and there's a path from Z to Y. Okay, so otherwise you have to write some kind of while loop at least for transitive closure, not to mention, efficient algorithm requires more things. So this is almost the core. This is the core of logic programming, except now you say, well, I'll give some facts. Like I know there's an edge from 1 to 2, edge from 2 to 3. I can even know there's a path from 1 to 2. And you can ask queries. Okay, what are the XYs such that there is path from X to Y? Okay, all pairs sort of. What are the X's such that there is a path from 1? What are the X's? There's paths 2, 3, and whether there's a path between 1 to 3. Okay, this is just how powerful logic programming is. You write the rules and you have some facts and you can do the queries. Okay, I only have one term, it's predicates. These edge and the paths are called the predicates. And there are only two kinds. The ones that's not in the conclusion, like edge, those are the base, and the ones in the conclusion, that's called derived. Okay, so I would like to use these rules, right? I said Python's great, I have everything, except I cannot use these rules. I have to write that while loop or call some libraries, but I have different, more complicated relationships, right? There's no library for those. Okay, but how do I do that? Well, because the applications need other essential, right? You have to have states and updates and modularity. And currently I have to use this. I have to, add some interface, some libraries, right? Just like you're using a database, using these database connections, JDBC and stuff. So something to import a library at least, or access a database, and then you have to convert the data, the facts, the queries, and then something gets done there. When you come back, you have to convert the results. Okay, and that's just a lot of boilerplate code. And of course, you can extend logic languages, but that's a lot more work. Okay, so here's Alda. Okay, I want to do all of them seamlessly. Just one example, it's a small portion of role-based access control. This actually is an implementation of an ANSI standard. Okay, and you can, again, ignore this because I realize there's some logic programming people that they don't understand anything about what's this, class or something. So just the idea is this is almost like Python, but I don't use a Python syntax in here. But you have components, right? Large system components. These are classes, core back and hierarchical. They were just classes that you can instantiate to become objects. So that's objects. And then for each of these objects, you keep some states like users and roles and user role pairs. That's a relation actually. And these are sets, empty sets start with. And everything you do on them is some updates, like here, this function takes a role and add a one to the set of roles, and some queries. And this one would return the set of users have this particular role, right? So essentially, database applications or any application you think about it, keep some states and some queries and updates. So the same thing in here, except this one extends this one, so it has all the state variables and had all the operations, but it can add more or can rewrite them. Okay, so this is just extends it and call the super, and then add a set of pairs, which are role hierarchical pairs. Some role inherits some other roles, and then you can do authorized roles, which are return a set of users, right? Not only directly have some assigned user role, relationships, but also some role in the middle, which you can use the transitive role hierarchy, right? You can inherit. And here are where the rules are. I need a transitivity. So this is copied from the previous slides. Okay, I just gave a rule set name called the trans rule set. And then this function, trans rule set function, actually just call infer. Okay, using this rule set I defined and setting edge, the predicates, okay, to be true for the set of pairs in the given sets, and then return the set of pairs for which path holds. Okay, and this one also union, the reflective just pairs in rows. So that's basically all the features, right? I already explained this is the rules, and then this is the infer. Okay, and so the only thing is you have to think the infer have to do something really smart. Okay, this was I described. Of course, you use a logic rule engine. Okay, This is really all. The key concept here is the sets, okay? The sets here, the set of pairs becomes something that the predicates holds, okay? So every predicate is like pairs or triples, just set of triples. You know, something is true for a set of tuples exactly when that tuple is in the set. So you don't need any interface, okay? This sets in the rest of the program exactly just become predicates. Okay, so that's the key idea of this integration. And the only other thing is, well, you can call query, I mean, you can do queries by calling infer and passing the data and get the result out. Okay, that's really the key idea. And then all this, you know, it's a variable, it's a predicate, the value can be updated. You can change, right? Change to the set of row. You can update this. Okay, and then by the way, these rules and these predicate, these variables, I'm sorry, here, the variables, they are just variables. They can be, you know, the object field, they can be here, they're local to this rules, or they can be global. Okay, the rules can also be, of course, global. Okay, and the only thing is you can have these predicates when they are global or they are object field, and you can update the base predicates and the derived predicates get automatically maintained. Okay, that's really all in there for this language. In fact, I just summarized the word. I mean, everything I said was exactly in here. The predicates are sets, and you can call it, you can update, then you can be any scope. Okay, the only thing I showed this example, this was copied from the previous slides. Now here is, instead of having path and edge or local variables, you can have object field, I call the trans RH. And since this is just field, I can use that to replace this function call. Okay. And then I can use this set of rules, okay, instead of this rules. So I don't have to pass in edge or pass out path. I just use RH directly, and I put the trans RH in here. And remember the reflexive roles, I just add in here. So you can actually remove this definition altogether. Whenever RH or roles get updated, the trans gets updated directly and used in query. Okay, that's just a summary of the result. All right, and so discussions. So these are just how you integrate rules with all of sets and functions and updates and objects. In fact, in our implementation languages support concurrent and distributed objects, and we have tuple patterns for writing those predicates, you know, tuple queries. And actually, there's something really complicated in logic programming called higher order predicates. But you get them for free. You don't even have to think about them. Okay, but the point is no interface code. Okay. And of course, have some prototype implementation, have some experiments with different types of applications just to show how easy to write them. The interesting part is, in terms of precision, is we actually have something we didn't implement, but we did decades of research before this. One is you can declare these predicates called actually just binary, certain or uncertain. Because remember, actually, we already have a couple of people talking different semantics, right? Mark talking about negation by failures or something. Really, when you have that rule saying path something if edge, okay? You don't need a fancy logic. Path if edge, okay, I get something path to be true. But what about the rest, right? Should they be true or should be undefined? If you don't say that clearly, of course you have different semantics, okay? And similarly, they do give all the rules, there are other rules. So the more interesting use of those is this. This is the most famous Russell's paradox, 120 years old, and not solved, solved, but everybody give different meanings, right? So what does it mean by solved? So barber shaves X if X doesn't shave X itself, right? Makes sense. Barber shaves your head if you don't shave yourself. Unfortunately, if you ask if barber shaves barber, that's barber shaves barber if barber doesn't shave barber. This is the most famous Russell paradox. I said that there are different meanings. It's not like program language theory, different, you know, operational semantics, axiomatic semantics, they agree, and here they do not agree. So how can I talk in this natural language or whatever? And even worse, by the way, this is actually simple after all. What's harder when you have actually, Michael was describing, you have aggregations, okay? And not just means count equals 0. So I made up this example, you know, Tom will attend Alpop if the number of people who attend Alpop is at least 20. Okay, think about it. Then this is again a trivial example. So if a lot of people attend, Tom will attend. If one person attends, Tom will not attend. What about if the 19 other people attend? Okay, again, there are 13 different semantics. The problem, they do not agree. Okay, but the point is, if you just make it clear, the binary clear, okay, I didn't expand all of them because that's the whole paper. And there's a trivial thing, actually, I have some fancy name, but just means iterate. It's just like the edge path example or solving constraints, and you match all those different semantics. So we have these papers. But most exciting actually was my work before all of this is efficient implementation. We want to automatically generate the code, and in particular, gave the complexity guarantees, and not just actually complexity, even constants cost. And in the sense you have to give, imagine back, give a sense of what this is optimal, the best you can do. And indeed, for the path example we just had, how long does it take to do the transitive closure? If you're in undergraduate algorithm textbook, they will tell you, and do the third, okay? But actually, the good ones will tell you it's actually n times number of vertices times number of edges. And most practical things, edge is sparse, so it's n, squared, okay? And that's just computing all. Now, if you can do query, I only want to find the ones that, there's path from 1 to 1. So you can actually guarantee generate the code that takes just number of edges. And in fact, if you process all the code and depending on the query, you can just say this is number of reachable nodes, right? The result size is optimal, okay? So actually, for the query part, this one we improved this famous, in case you heard of the magic set, exponentially. In fact, this is Tunji's thesis work. Okay, and we have, of course, this is my work from a long time ago, a lot with my students and joint co-authors. Okay, and that's all for mine.